Kind of interesting looking liquid, isn't it, Kristen?
Yeah, it looks like it's boiling.
Yes. Matter of fact, it is. But here, take this carnation and dip it in the boiling liquid, and you'll swish it around a little bit like that. Then I want you to take it and hit it on the table there as hard as you can.
Okay.
Go ahead.
Can I hit it now?
Yeah, go ahead. Just bang it hard.
Hey! What happened?
Well, what you did was to freeze that flour, because what we have here is liquid nitrogen.
Oh, I thought it was boiling water.
Yeah, it looks like it was boiling water. That's because I just poured it in, as you saw. And actually, the heat of the table and the heat of the glass bowl are actually boiling it, because they're raising it to a higher temperature. 290 degrees below 0 centigrade.
Oh, that's quite
Very cold. So obviously, I don't want you to put your fingers in it.
Okay.
And that's why I had you put on the safety glasses.
Okay.
Because it's a lot of fun to play with it, because you can do all kinds of interesting things by taking everyday materials and putting them in there. There's a piece of apple.
Okay.
And here is a hot dog.
Okay.
I'll put that in there. Piece of rubber tubing.
Mm-hmm.
Ball. And this piece of solder.
Okay.
You know what solder is?
No idea.
Well, solder is a very soft material that is used. It has very relatively low melting point, so they use it to attach wires, and the soldering iron comes down, it touches it, and then it changes to a liquid, then it freezes quickly, so it holds it in there. But the point is, it's very soft. So let's start with that. Have you ever made a spring?
No.
Well, I'm going to make a spring out of the solder. Watch. Like that, see?
Oh.
And then, if I make a little hook on the end down here, I can put this nut on it, and you will see how non-springy it really is.
Yeah.
Okay, now I'll stick it all back together, and we'll stick that in the liquid nitrogen.
Okay.
Boiled it again because it was hot enough. Now, I don't want you to put your fingers in, so here, you take these long tongs and put the hot dog in.
Okay. Whoa.
That's boiling too. Now put the rubber tubing. Okay, that's floating along there. Now there's half an apple. Put that in.
Okay.
And finally, just to make sure that you understand what this is, you want to back up and bounce that on the floor fairly hard. And we'll catch it. Okay. Rubber ball. Put that in. Okay, now you see all of those materials, even though they're at normal temperature, are actually making the liquid nitrogen boil. Now, have you ever seen a gas that's in liquid form before? Ordinarily, this material...
Gas? Normal gas, car gas. That's in liquid.
Oh, I see. But this is a gas by chemical definition or physical definition. A gas is something that fills up a container like air. But this is now... In fact, to make this, they take air and they squeeze it and take away the heat to make both the nitrogen and the oxygen in the air in liquid form. Then they can take off the oxygen part and keep that separate, and the nitrogen is what's left behind. So now we have something that is ordinarily a gas at normal temperature. It is now a liquid. Do you suspect what you're going to do with the hammer?
Yes.
Put on a, well, I don't think you probably need a glove, but it won't hurt to put it on. And I'll bring out each one of these items and place it there on the table, and you hit it with a hammer.
Okay.
First of all, you know how the rubber tubing was real bendy?
Yeah, it was.
Okay. I'm going to put it down there on the table, and you hit it with the hammer. You ready? Give it a good whack. Go ahead, whack it.
Oh my God.
1,000 pieces. Now, so you know what happens to rubber at lower temperatures?
Yes.
Yeah, obviously it got very stiff, didn't it? Remember I told you not to put your finger in? Well, let the hot dog represent your finger. Give that a good smash with a hammer once. Another 1,000 pieces.
Oh my God,
Yeah.
I can't believe it.
Half an apple coming up. Are you ready?
Yeah, I
Whack
suppose.
that. There goes an apple in it. In fact, powdered apple we have here, frozen. Now, you
Wow.
remember that spring I showed you of solder? Okay, I'll get it out
So,
and hold the end, and you put the weight on the end of the little hook.
Okay. Hey, it's not at all as bouncy.
No, it's real springy now because obviously, what have we found out about these common materials when you put them in something and get them real cold?
The substance itself gets so cold that it gets frozen in a way.
Well, it's
not
sort
as
of,
flexible.
yeah. It's not as flexible. In other words, when you get something very cold, like the whole molecular structure changes, and it changes completely. So things like the rubber tubing are no longer flexible, but now are very stiff. And people have noticed that when they go to the Arctic, some of their materials will change very definitely. Anyway, it's kind of a lot of fun to play with. And now I'd like you to put on this glove, because I'm going to hand you that ball.
Okay.
First of all, let's take a look at it. Remember how it was nice and round before? Why has it got a dimple in it? What was it filled with before?
Air.
Oh, so what must we have done to the air inside? Just shrink it, it takes up less space, right?
Yeah.
So the outside air pressure pushed it, and it's now got a big dimple. And you think you know what's going to happen when you throw it?
I've
You got a pretty good idea?
Yeah.
Okay. Here you go. Just hard as you can, and I'll catch it. Ha-ha.
Uh-huh.
Yeah.
Oh my, it used to be so flexible and
Yes,
bouncy.
it used to be. But there it is. Feels like a piece of potato chip. Anyway, that's fun. You can tell your friends you've now experimented with a liquid nitrogen bath in which things change very dramatically. Lala, here's one of my favorite sweaters, and I would like you to put it on, please.
Okay.
Maybe a little big, but we're going to do a sort of magic trick that has to do with sweaters.
Big.
Yes, it's big. Okay. Now, we want to be sure to mark the front of it, so would you put a great big X with this tape on the front of it?
Okay.
Okay, now hold out your hands, because I'm going to tie them together.
Why?
Well, once I've tied them together, then I want to challenge you, I hope this is a challenge, to take the sweater off, turn it inside out, and put it back on again.
I don't think I can do that.
You don't?
No.
Well, as a matter of fact, it's possible. And it's all based on a scientific principle that is investigated by mathematicians who investigate topology, the study of surfaces.
Oh.
You can take that sweater off, turn it inside out, and put it back on again.
If you say so.
Okay, well, first of all, take it off.
Okay.
Okay. Now, pull your hands out like that. Okay, now you've taken the sweater off, and it's inside out. Mm-hmm. Okay, now, all you have to do now, however, is turn it inside out while it's there on the ropes. Then when you put it back on, it'll be the right way. In other words, let's straighten it out. Here's what we do. Here, I'll start with this sleeve. See what I'm going to do?
Oh, I see. You're going to pull it through.
Pull it through the sleeve, yes. Yeah. So you keep pulling up there, and I'll keep pushing from the other end.
There's the X. Get it out. Yeah.
Okay, now where are we?
Okay.
Okay, we got to get this sleeve pulled over here like this, and then I'll get both of them right there. Here.
Okay. Well.
Now.
It's backwards.
It's backwards. Yeah. However, when you put it back on, here's the X. See, it's backwards. It's on the back side.
Oh.
So now I'll put it back on, but in order to get it back on, you're going to have to put your hands through the sleeves, right?
Okay. There's one.
Okay. Okay. Now, can you get it on?
Oh, I think so.
Where's the X?
Right here.
So it's inside out. You took the sweater off, turned it inside out, and put it back on again inside out.
I didn't think I could do it.
Well, now this works very well with a sweater that you get a letter on for athletics or cheerleading, because you sew it on the front. So if it's big enough, you can take it off, turn it inside out on the rope, and put it back on. So try that with some of your friends.
Okay.
Now I'll take the ropes off.
Thank you.
These are stiff spikes from the tips of a plant that looks like corn. The plants are said to have been brought from Europe to North America by Benjamin Franklin. By machine, the spikes are processed, bundled together, trimmed, and a handle added. You sweep away dirt with the spikes of the broomcorn plant. Darren, here's a little gadget that has a little switch down here. And if I'm going to turn it on, it's going to run across the desk here like this. And if it gets into any kind of trouble, all you do is clap your hands.
Okay.
Clap your hands. You know what that is? That's a single sensor robot.
Okay.
What's a robot, first of all?
Well, a robot is a machine that does things for people. That it does chores or...
Chores?
Yeah.
Have you seen them in pictures in the factory?
Yeah, they're just working and doing one special function.
Right. Take a plate up and turn it over or do something like that. And a single sensor robot, what does that mean to you?
Well, it probably senses one thing.
Only one thing. Now, you already know what this one senses, right?
Yeah, it senses sound waves.
Sound waves. In fact, this little thing in the front here is a sort of bumper, so it bumps into things, but when it hears that sound, it sends a signal down over here to the microprocessor inside, and at the bottom, you can see there's a motor, and it'll always turn 30 degrees and then keep going.
Okay.
So this time I'll see if I can set it so it hits the wall over there.
Okay.
You know how to save it from
just clap
falling
my
over the
hands.
precipice over there at the edge of the desk? All right.
Okay.
I'll let it bump into my hand this time. Now you're cooking. Okay, now how would that be useful in a robot that you might have around the house? The idea that it responds to sound.
Well, in case it bumps into something, so it can bump into something, so in case you want it to deliver something or things like that.
Right, so it bumped into something, that would be one thing, but it also could be sensing to other kinds of sounds. You could say, robot, come here.
Okay,
And maybe someday
it'll pick it up through here.
they'd pick it up through there and it would do various things. So that's
Okay.
one based on sound. Here's another one. This is an odd one.
Looks like a spider.
Yeah, doesn't it look like a spider? Has 6 legs. Well, turn it on and see if you can figure out what it does. You see the switch there? Let's let it walk all the way to the wall once and see what happens.
Oh, I see. You're putting your hand in front of it, and it blocks it out so it turns.
Yes. Okay, put your hand in front of it now. Can you grab it? You turn it off? And what do you think this single sense is in this computer?
Well, it's a seeing sense. It's
seeing sense, yes.
Yeah.
But it's not seeing just regular light like you and I are. Inside here is a sensor that responds to infrared. You know what that is?
Okay. I think it's when it sees, it's a wave that it sees.
True, but then light is a wave too. This is a wavelength of light that we can't see.
Okay.
It's too long for us to see. Our eyes aren't sensitive to it, but the little sensor in the front does, and if you turn this one over, you see it has
A motor.
the
Two motors.
Yeah, to work all these 6 legs. Now, if it's true that it sees things in infrared, what should happen if we take this transparent plastic like that?
Well, it'll probably try to keep going right through.
Why? They're trying to keep going through. There it is, right in front of it. Why can't it see it?
Well, because it's transparent.
Yes.
And it sees whatever's behind it.
Yes, it's transparent. Now, how would this be useful in a robot around the house?
Well, if it sees things, it'll stop, and it can, like, it won't bump into walls or anything, and...
Except if they're transparent walls,
yeah.
like that one, right?
Yeah.
Okay. So that might be a useful one to have. Now, over there on top of my computer, you see that piece of paper? Bring
Yeah.
it down here and put it on the desk.
Okay.
What do you suspect this computer is going to do, or this robot's going to do?
Well, judging from the paper, I think it'll follow the black line.
Well, before we turn it on, see if you can figure out how. You see right over here,
Well, there's a couple of sensors
there's a couple of sensors right there. There's one in the middle and one on each side. As long as the black line is going along here, it'll go straight. But if it starts wandering around, or the line does, this sensor over here will detect the difference between the black and the white and send a signal over to the motors on the other side and straighten it out again. Then this one will take over. So it should follow the line, you think?
Yeah.
Okay, turn it on.
Okay.
There it is, switches right there.
Okay. I see, so it's switching back and forth to each sensor, and it's following the line.
I don't know if you've seen robots that work on this principle in some hospitals and in some office buildings. They have a gadget that delivers the mail. So one day, you'll probably have robots that have computers in them that will, in effect, do some things that are around the house. And it might work on a sensor like this one, which is what?
Infrared.
Yeah, or infrared. Or a sensor like this one.
Hearing.
Yeah, or sound.
Sound.
Or a sensor like that one.
Yeah, with the two sensors that judge the light.
All right. These students are at a very unusual school. They're waiting in the shade because this is Texas in midsummer, where it can get very hot. But it will get even hotter for the students. They wet down their protective clothing, an instructor starts the session, and the students will begin to put into practice what they've learned in the classroom. The students are professional firefighters taking advanced training. The objective of this exercise is to advance on the fire as a team. They take small half steps to keep from tripping. If one man falls, the whole team could go down. Even though this is a practice fire, fighting any fire is dangerous, and instructors keep an eye on the team. They move slowly, putting out the fire as they advance. If they move forward too fast, the fire could reignite behind them, and that could be disastrous. The session continues until the fire is out. After all the teams have had their turn, the students and the instructors discuss their performances, trying to learn from each other. Then, they get instructions for fighting another kind of fire. Each summer, nearly 3,000 professional firefighters come from all over the world to Texas A&M University to find out how to handle fires they may have to fight at home, fires that require special techniques. The school provides the unique facilities to practice those techniques. Under the supervision of expert firefighters and fire protection engineers, the students learn how to put out actual fires in the classroom and then by actually doing it. The facilities include the deck of a ship, a tanker truck, a crashed plane, and an oil storage tank. They even have a special course in how to handle a fire at a nuclear power plant. The firefighters learn how to work safely and effectively in these special situations. If you should become a firefighter, you too may practice putting out fire at a firefighting school. Sort of a pretty sound, isn't it, Eugene?
Yes, it is.
Yeah. So here, just rub your finger over the top of the glass.
Nothing happened.
Now, the reason is probably because what we really want to get the glass to do is to vibrate, right?
Right.
And in order to get it to vibrate, you have to sort of give it a little push and then not a push, and then a push and not a push. If you know how a violin bow works, where they put rosin on it, and so it scrapes along the string, well, that's what you have to do with here. And the problem with your finger, it probably has some oil on it. Everybody has oil on their fingers. So here's what you do. Take some of this stuff.
Vinegar.
Yes. You dip your finger in the vinegar, and that cuts the oil that's on your finger, so it should stick and slip over here on the top of it. So try dipping your finger in the vinegar, and now rub it. Aha.
Makes
Now,
a sound.
why is it making a sound now?
Well, like you said, it sticks and...
It sticks and slips, right?
Yeah. and that causes the glass to vibrate.
Right.
And with the water too, and it makes a sound.
Okay, so the more mass that vibrates, the lower the note.
Right.
Okay, well now dip your finger in it each time and go ahead and play my series of glasses and see what you get.
Okay.
Wait a minute, wait, come on, dip your finger in. That one didn't sound too good. Go ahead, play it again.
This one's too high.
Okay, what do I do?
Well, we pour more water into
Okay,
it.
dip your finger in there and keep playing it. Just maybe these two is all you need, right? Try that.
This one's still too high.
Close enough for now.
Yeah.
Continue. Now notice this glass, in spite of the fact that it's almost full to the very top, it's the high note. So when you try this at home, you got to, experiment and practice. And what's the secret ingredient?
Vinegar.
Vinegar. And you hold the bottom of the glass and rub it like this to get a beautiful sound.
It's just a potato just kind of floating right in the water.
Right. It's halfway up or halfway down, depending on your point of view, right?
Yeah.
Okay, that's my challenge for you, Scott. I want you to be able to duplicate that. Get a potato to float halfway up a container like that. Well, here, let's start from the beginning. Cut the potato in half.
Okay. There you
And
go.
put it in here.
Okay. Just sinks to the bottom.
Okay, that's a potato in water.
Okay.
Take the other half and put it in this container.
It just stays at the top.
Yes. Now, what this is water with a lot of sugar dissolved in it.
Okay.
And I like sugar better than salt because it dissolves faster and you can't really see it. It doesn't look, it looks like plain old water.
Okay.
Now, why does it float on the sugar and water and not on the regular water?
Because the sugar water makes kind of like the water thicker, so it'll
That's
stay
right.
there.
It makes it sort of thicker.
Yeah.
Actually, the correct term is more dense. The more
Okay.
sugar you put in, the more... In fact, you could do it with syrup. It really would float real high, couldn't
Yeah.
you? So what you're doing is making sort of a syrup. Now, the problem is, how are you going to get a container half sugar water, half regular water? That's what I have over there.
Okay.
Okay, here's what you do. Pour
Potato in there.
enough sugar water till it's halfway full. Go ahead, pour it in there.
Okay. That's about
A
halfway.
little more, a little more. Okay, now the problem is, you've got to get regular water on top of that. Here, so tip the beaker like this,
Okay.
and carefully as you can, pour the water down the side.
Okay.
Slowly, as slowly as you can. Because what you're trying to do is prevent them from mixing, so that you get a layer of plain water on the top.
Okay.
Keep going.
It's kind
It
of
is
cloudy in there.
Yeah, well, that's kind of where they're mixing, and you want to keep that to a minimum if you can. Very slowly, slowly. Okay, that ought to be enough. Now, set it down and let it settle.
Okay.
Now, see where it's floating?
Yeah, right in the middle.
Where must the sugar be?
The sugar's probably right about
Yeah,
there.
right about in here
Yeah.
someplace.
And the important point is that you pour it very carefully. Now, if you let that sit long enough, Scott, a process called diffusion would take place. You know what that is?
No.
Where the molecules move around, eventually it would all become the same.
Okay.
And whether it would float or not depends on how strong you made the sugar solution.
Okay.
But there's a nice trick. You can have that sitting on your desk and have challenge people to figure out how you were able to make a potato float halfway up or halfway down.
Okay.